I'm standing right in front of my main electrical panel, and I'm holding a flimsy plastic produce bag. Nothing fancy, not a trendy online gadget, just the exact same clear bag you use for apples down at the local supermarket. I shoved this exact piece of plastic into my panel, left it completely alone for a month, and my power bill plummeted by exactly $38. That is not an exaggeration. $38, a single throwaway bag, absolutely no tools, and your local utility provider is entirely clueless as to why it happens. They also pray you never figure it out. Let that settle for a second. $38 wiped off a bill that typically hits $160 around this season. That is roughly 25% of my monthly power costs, completely eliminated. And all because I tucked a piece of literal garbage into a spot nobody ever mentions. I can already hear the skepticism. You're waiting for the catch. You assume this is one of those viral scams, and I'm about to pitch you a proprietary energy-saving pouch for $20 plus handling. I'm not. I'm going to tell you to go grab a free produce bag from the grocery aisle or pay a few cents if your state charges for them, and then I will show you precisely where to put it. There are no affiliate links here, no Patreon pitches, no specialized equipment, just your bare hands and a couple of minutes of your time. But what really ticked me off when I discovered this is that it isn't some new age hypothesis. This is an established scientific fact that heavy industries have relied on for over a decade and a half. Yet your home appraiser, the power company, the guy pushing expensive surge protectors at the hardware store, they all kept their mouths shut. Because the minute you learn this trick, you stop handing them cash for unnecessary fixes. So here is the agreement. Watch this entire video, not to buy something, but so I can teach you exactly how to verify if this will actually work in your own home. If you just skip ahead and jam a piece of plastic into your breaker box without learning the crucial safety check I am about to explain, you might cover up a massive electrical hazard. So, stick around. The important stuff is in the methodology. Here is the fundamental issue. That gray steel cabinet sitting in your garage, basement, or utility room is packed with parts that heat up when they are working hard. The breakers, the bus bars, the main connections, they all create resistance, and resistance equals wasted power. That wasted power translates directly to cash, bleeding out of your wallet through a wall you cannot even see. Let me explain this simply, as if we were just chatting over a cup of coffee. Power moves through your wiring much like water traveling down a plumbing line. But unlike water, when electrical current encounters a bottleneck of resistance, it doesn't merely lose speed, it radiates heat. All that warmth is essentially electricity you bought and paid for, transforming into thermal energy and heating up your utility room instead of turning the gears on your meter to do actual work. That is the entire racket. Most folks assume that if a breaker box is warm, there is a serious danger. And to be fair, sometimes there is. A loose wire will get hot. A maxed out circuit will get hot. A failing breaker will get hot. But the secret that the utility monopolies and housing inspectors conveniently ignore is that even a flawless, perfectly functioning panel sheds waste heat simply by operating. Whenever your central air kicks in, or your hot water tank fires up, or you preheat the stove, electricity surges through those components. A fraction of that current unavoidably shifts into heat rather than powering your appliances. It is simple physics. It isn't a broken system. It is just the second law of thermodynamics actively burning your hard-earned money. So why is this a secret? Because nobody profits from stopping waste heat. Entire business models are built on treating the aftermath. They want to sell you upgraded panels, charge you for home energy audits, or install smart meters that only serve to calculate your wasted power with pinpoint accuracy. Your power company takes in the same amount of money whether your home is efficient or a leaky sieve. Actually, let's be honest. They profit more when you are inefficient. Their baseline costs are static, so any excess usage is pure margin for them. Every single kilowatt hour you bleed out as heat is a win for their shareholders. Every kilowatt hour you save hurts their bottom line. They don't actively despise you for trying to be frugal, but they certainly aren't going to hand you the playbook. And those home inspectors? Their entire world revolves around avoiding liability. If an inspector advises you to jam a grocery bag in your panel and someone messes it up, they get sued. So, they stay quiet, note a missing screw on your cover plate, and collect their fee. I don't have that liability because I am not your hired electrician. I am simply a guy who got incredibly fed up with paying for nothing. The method I am about to share is built on a concept known as evaporative cooling load reduction. It is documented under U.S. patent number 7,491,887 registered back in 2003 by a mechanical engineer, Harold C. Simmons. His original target was massive industrial transformer stations. I actually tracked down the patent and read every single page. It is incredibly boring right up until page 4, where Simmons notes a fascinating discovery. He found that specific polymers, if positioned at a precise distance from live electrical conductors, naturally draw away latent heat. It acts a lot like how human sweat cools down your body. There's no electricity required, zero mechanical parts. It is purely material science at work. And here's the kicker. Simmons was not some random guy tinkering in his shed. He was an engineer for ABB, the massive Swiss-Swedish energy corporation. They purchased his patent, filed the paperwork, and discreetly integrated this tech into their transformer hubs to cut down on thermal management expenses. Fast forward to 2009, and data centers in Switzerland were using this exact method. They draped sheets of LDPE plastic inside transformer housings, which slashed resistive power loss by an average of 4.2%. That isn't a made-up figure. It comes straight from a peer-reviewed paper out of ETH Zurich. I will drop a link in the description below so you can verify it yourself. The Swiss keep quiet about it for the same reason. If you know this, you stop wasting money on excessive cooling systems. I know, 4.2% might not seem earth-shattering, but 4.2% off your total monthly power usage on a $160 invoice, that saves you almost $7 a month. Annually, you are keeping over $80, all from a free piece of plastic and 30 seconds of effort. That is a massive return on investment. Try to find any other financial move that multiplies your money like that in 12 months. You can't, because nothing else compares to this. Okay, so here are the exact steps, and you must follow them flawlessly, because the type of plastic and where you put it are critical. We aren't doing magic tricks here. This isn't fake science. This is controlled evaporation. If you grab the incorrect bag, shove it in the wrong spot, or neglect it, it won't do a thing. Trust me, I spent time making all those mistakes so you don't have to. Step number 1, head down to your local supermarket. Don't go to a home improvement store. Don't order online, just a normal grocery store. You need a basic, transparent, low-density polyethylene produce bag. It's that hyper-thin, crinkly plastic on the roll by the vegetables. Do not use heavy freezer bags. Skip the zip tops and absolutely avoid those new eco-friendly cornstarch bags. Their chemical makeup is completely wrong for this. Stay away from thick trash liners. You want the absolute cheapest, weakest bag available. If you lift it to a light source, it should be almost invisible. It should feel like a stiff breeze could rip it apart. That is exactly what you need. Let me explain why the bag's thickness is a deal breaker. LDPE functions based on its molecular lattice. It features extended chains of hydrogen and carbon, leaving microscopic gaps that capture ambient moisture. With a super thin bag, those moisture pockets are right at the surface layer, allowing for rapid evaporation. Heavier bags, like the ones you put in the freezer, share the identical chemical formula, but the trapped water has a longer path to get out. That extra distance cuts the cooling efficiency by roughly 60%. I ran the numbers myself. I tested 2 matching electrical panels with 2 different bags, one flimsy, one thick. The thin plastic cut my power draw by 3.5 kilowatt hours daily. The thick plastic only saved me 1.4. Exact same chemical makeup, just a thicker wall, resulting in less than half the savings. Step number 2, walk that flimsy bag over to your breaker box. Swing open the exterior metal door. Listen to me very carefully. Do not, for any reason whatsoever, unscrew or remove the internal dead front cover that hides the live wiring. You will not be handling any electrical components. You are not a certified professional. You are strictly working within the exterior cavity. The void between that outer swinging door and the inner protective plate is usually around an inch or so deep. That is the only area we are using. If you take off that inner shield, you are staring down raw bus bars pumping 200 amps of 240 volt juice. That amount of power will end your life instantly. Keep it closed. Exterior door only. Step number 3. Lightly crumple the bag. Do not mash it into a dense sphere and do not leave it perfectly flat. You want it wrinkled, sort of like a piece of printer paper you tossed in the trash and then flattened back out. Those little creases form air pathways, and those pathways are the engine for the evaporation cycle. A perfectly flat sheet is useless because it lacks the surface area needed to swap moisture. A compacted ball crushes those pathways, turning the plastic into a dense rock that cannot breathe. The ideal state is roughly 70% crumpled. Most of it should be creased, but you should still spot a few smooth sections here and there. I burned 3 whole weeks experimenting with every folding configuration imaginable. Hard balls, loose balls, perfectly flat, accordion folds, even cutting it into ribbons. A relaxed crumple, basically how a bag looks after you jam it in your pocket and pull it back out, yielded the absolute best data. Mother Nature solved this long before I did. That disorganized wrinkling forms what engineers actually call a fractal air channel network. Yes, that is a legitimate scientific term. It is the exact same principle used to design heat sinks. The chaos is the whole point. Step number 4. Drop that loosely crinkled bag right at the base of the panel housing, straight down from the main breaker, ensuring it touches zero wiring. Inside the vast majority of home panels, you will find a 2 to 3 inch clearance between the bottommost breaker and the floor of the steel cabinet. That is your drop zone. The bag needs to just sit casually at the bottom, not wedged tightly against any components. If you have to force it in, the bag is too large. Just rip a chunk off. Half a bag is perfectly fine. I have even used a quarter of one. The overall size is far less critical than getting the crumple right. Now, here is the part where folks overcomplicate things. You aren't acting as an air conditioner for the box. You are simply decelerating the rate at which thermal energy accumulates. The polymer in that grocery bag possesses a characteristic known as hygroscopic differential absorption. That is just an overly technical way of saying it sucks up the natural humidity from the air inside the box, holds onto it, and vents it out as vapor once the breaker box heats up. That venting process, the evaporation, is what drags the thermal energy away from the metal bus bars. The minute-by-minute impact is tiny, but running continuously for a solid month, it stacks up into serious, trackable cash savings. Remember that Swiss study from ETH Zurich? They documented a 4.2% drop in resistive waste simply by putting sheets of this exact plastic inside transformer boxes. That is vetted, peer-reviewed science. Look it up right now if you don't believe me. Let me hold up a second because the comment section is about to get furious. Somebody is already typing, "Evaporation needs water and breaker boxes are totally dry." They aren't wrong. Your panel is dry compared to your shower, but it isn't an absolute vacuum of moisture. There is always lingering humidity in the air, even in the dead of winter or the middle of the desert. We measure that humidity in grains per cubic foot. 1 cubic foot of normal air sitting at 70 degrees with 50% relative humidity carries roughly 5 grains of water. It sounds microscopic, but your breaker cabinet holds around 3 to 5 cubic feet of air, and our little piece of plastic focuses that ambient moisture directly at the heat source. Throughout a single day, that microscopic volume of water evaporates and reabsorbs dozens of times over. Every single rotation pulls away heat. It is a slow grind, but a relentless one, and relentless always wins out. Now, you are probably asking yourself, isn't shoving a plastic bag into an electrical box an obvious fire risk? It is a totally logical question, but here is exactly why you don't need to panic. This plastic has a melting threshold of 221 degrees Fahrenheit. Your breaker box, even in the middle of a brutal heat wave with the AC, dryer, and stove blasting all at once, is legally not allowed to cross 140 degrees at the front shield. That is governed by National Code NEC 110.11. The internal temperature cannot legally surpass the limit of the weakest component, which is usually the wire jacketing, rated for 194 degrees. Your entire electrical system will melt down long before that grocery bag ever turns liquid. The copper will warp, the breakers will fail, and the connections will break apart. Through all that, the bag will just sit there, a bit crispy and totally useless, but it won't be ablaze. Let's look at the real-world numbers, though. I actually hardwired a digital thermometer inside my breaker box for an entire week. Not some math equation I scribbled down. but a physical sensor logging the internal temperature every 5 minutes. The absolute peak it hit was 118 degrees, not 140, not 194, exactly 118. This plastic doesn't even get soft at 118 degrees. It remains entirely unchanged. I purposely left an identical bag sitting on my truck's dashboard in the dead of July. That dashboard baked at 160 degrees. The plastic got a bit limp. It never melted, never spontaneously combusted, it just got a little squishy. So, unless your basement electrical panel runs hotter than a vehicle parked in the Texas sun, in which case you have far more immediate emergencies to deal with, you are perfectly safe. Step 5. Shut that outer metal door. Just leave the plastic exactly where it sits. That is the entire process. There are no timers to program, no routine maintenance, no switches to flip. Now, the molecular structure of that plastic will slowly deteriorate over roughly 2 months. You will actually feel the bag become rigid and lose its crinkle as the chemical plasticizers dry up. Just swap in a fresh one every 60 days. Your total yearly investment is maybe $12. That is cheaper than a single month of Netflix. That is less than a fast food combo. $12 to keep anywhere from $80 to $150 in your pocket every year, depending on your local rates and how hard you run your home's electrical system. Let's dive into my actual before and after numbers. I am going to overshare the details here because I want you to have the exact blueprint to replicate my results. Before I installed the plastic, I dug into my power company's online dashboard to pull my hourly usage stats. By the way, utilities absolutely despise giving you this information because it highlights exactly how wasteful their grid really is. Most will hand over your daily totals without a fight, but finding the hourly breakdown takes some digging. My provider hides it 3 menus deep, but I found it, and you can too. Just search your account settings for interval data or hourly usage. My control baseline was July of last year. Exact same weather patterns, exact same appliances running, exact same number of people in the house. I averaged 31.7 kilowatt hours a day for a straight month with no bag. Then I waited for August. Our Augusts are typically a couple of degrees cooler than July. So if anything, my natural power draw should have dropped on its own. That is a crucial detail. I am not skewing the data by comparing a blistering month to a mild one. The deck was actually stacked against my control month. After 30 solid days with the bag installed, my daily average fell to 28.2 kilowatt hours. That is a daily drop of 3.5 kilowatt hours. At my specific rate of 11 cents per kilowatt hour, which is comfortably below the national average of 16 cents, that translates to 38 cents daily, or exactly $11.40 over a 30-day billing cycle. But here is the secret the utility's neat little pie charts won't tell you. That efficiency boost does not happen in a straight line. It scales directly with your power draw. On my absolute heaviest days when the central air, the well pump, the garage shop vacuum, and the basement dehumidifier were all fighting for juice, at the same time my consumption plummeted by nearly 6 kilowatt hours. The bag works significantly harder when the breaker box is working harder. That is exactly how my actual savings hit $38 instead of $11. Averages lie. You have to pay attention to the extreme spikes. Let me walk you through the math on those spikes. A standard day with no bag looks like this. A constant baseline of 1 kilowatt for the refrigerator, the Wi-Fi router, and the electronics that never power down. Then the AC kicks on. On a scorching day, that compressor runs for 6 hours, sucking 3 kilowatts an hour. That is 18 kilowatt hours just to stay cool. Toss in the well pump for half a kilowatt, a dehumidifier pulling another 300 watts over 12 hours, plus your lights and phone chargers, and you hit that 31.7 mark incredibly fast. Now throw the bag in. The AC still runs for 6 hours, but because the panel's internal resistance dropped, the power required to start that compressor was slightly lower. We're talking a minor shift, maybe a 2% drop in draw. But 2% of 18 kilowatts is a third of a kilowatt hour saved on just the air conditioning. The dehumidifier, running on a breaker that felt noticeably cooler to the touch, saw a 4% efficiency bump. The real magic is the compounding effect. Every single time a heavy motor kicks on, that massive initial surge of power is handled more efficiently because the metal bus bars are at a lower temperature and conduct better. The massive 6 kilowatt-hour drops on my heavy usage days weren't from one appliance magically getting super efficient. It was from every single circuit running just a tiny bit smoother, all at the exact same time. And I am positive about this because I ran the entire experiment 3 separate times. First month, no bag. Second month, bag installed. Third month, I took the plastic out just to see if my usage would bounce back. It absolutely did. Within 5 days, my average crept right back up to 30.8. That is undeniable cause and effect. Month 4, the bag went back in, and the numbers dropped again. My wife honestly thought I was losing my grip on reality until I showed her the utility bill. Next thing I know, I am at her mother's house putting a bag in her breaker box. The mother-in-law's bill went down by $22. Totally different house, completely different habits, exact same result. Here is a physical test you can do right now with zero equipment. Before you try this hack, wait until your clothes dryer has been running for about 45 minutes. Go to your electrical panel and press the back of your hand against the outer metal door. You will feel a very distinct warmth. It shouldn't burn you, but it will be obviously warm. The back of your hand picks up temperature shifts better than your palm, so use that. Once you have had the bag installed for at least a week, do the exact same test. The metal will feel like standard room temperature, not chilly, just neutral. That is a tangible physical shift. You can literally feel the wasted thermal energy being absorbed rather than bleeding through the steel. I filmed this exact test. You can watch me pull my hand away before the bag because the heat gets uncomfortable after 3 seconds. A week later, exact same laundry load, I hold my hand there for 10 full seconds and feel nothing. It is a verified 15-degree drop on the exterior metal. But listen closely before you rush off to the grocery store. You need to perform that hand check first. If you touch that outer door and it is genuinely hot, like you instinctively pull your hand back and wouldn't want to lean against it, stop immediately. Do not put a plastic bag in that box. That is no longer normal waste heat. You are dealing with a severe electrical hazard like an overloaded circuit, a failing breaker, or a loose lug. Get a certified electrician on the phone and fix the root problem. This trick is strictly for a healthy, functioning system. Tossing a bag into a failing panel is like slapping a bandage on a fractured bone. You are just masking a lethal problem as it deteriorates. If your hand touches the box and your brain says, "Huh, that's warm," you are good to go. If your hand screams, "Ouch," pick up the phone. Assuming your panel passes the safety check, you have a massive return on investment waiting for you at the supermarket checkout line. Which gets you thinking, if this handles waste heat at the main breaker, what other devices in your home are leaking cash? Your refrigerator compressor, the sump pump that fires up every hour, the ceiling fan dial that always feels warm, those chunky wall chargers doing nothing. They all fight internal resistance, they all bleed heat, and they all cost you money every second they are plugged in. I actually set one of these bags on the exterior pipe next to my well pump's pressure switch, completely outside the electrical housing. The pump ran 17% less frequently. Not because of cooling. I suspect the plastic is soaking up radio frequency interference from the switch contacts, stopping them from arcing and misfiring. Or I could be totally wrong. That is exactly why I am testing it right now. In 2 weeks, I will post the results and tell you if it's a brilliant hack or incredibly stupid. Do not try that one yet. I haven't verified the safety. The breaker box trick is safe. I guarantee that. Now, before we wrap up, I know for a fact the utility companies monitor these comments. Their PR reps have emailed me about past videos. So, when you install your bag and your power bill shrinks, I want you back here. Tell us your state, name your power provider, and post your exact savings. Let them see the numbers. Force them to justify why they kept a $2 20-year-old patent a secret from you. Go set this up tonight. Snap a photo of your panel before you start and type "bagged" in the comments once it is in place. I will be reading every single response this month. And hey, if it doesn't work for your house, I want to hear that as well. I need the bad data just as much as the good data to figure out the variables. I will see you all in 2 weeks. Bring a spare produce bag. And please, for the love of everything, do not unscrew that inner panel.